Now to the normal. First we define it, then we try to work a little with it. This is how it looks. For instance, this is actually the standard normal that has a center in 0 and that actually goes like this, such that when you're out into plus minus 3, basically it's down at 0, at least almost. Here is the density function for a general normal. The standard one is the name for the one where this mu is 0 and this sigma that we see twice in the formula is 1. This is a function that has the form that I showed you. It's a so-called bell-shaped symmetric function, centered in the mean and going it's centered in the mean, and then it goes mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. So there are different ways of saying it. In a way, there is only one normal curve. If you see it generally like that, the normal curve is centered in its mean. What do I mean by that? Why do I say this stupid thing, mu equal mu, sigma squared equals sigma squared? Any idiot could have written these statements and known them to be true. But when we do this, it's because there are actually two different mu's and two different sigmas in what I have shared with you so far, right? Just a few minutes ago, I shared with you a mu and a sigma that was the formal mean and variance of a continuous distribution given by an integral of something, right? Now I give you a functional expression. It's a function of x, yes, but there are two unknowns in this function, the mu and the sigma. So there is a mu and a sigma in this function. As it appears, these names are chosen wisely for those unknowns in this function because they are chosen in such a way such that if I do the integral to find the mean, it appears to be the mu appearing in this function. So the choice of names match, right? And also the variance, the way the sigma is named here matches the fact that if I do the integral, is actually the variance of the variable that I see as an unknown in my density function. So it's a density function, it's a function of x, but with two unknowns, the mean and the variance of the probability distributions. What I mean by this is, I'm showing you a few slides and then we try it in practice. In fact, there is only one normal curve. If you're willing to rescale and move your plot a little bit, there is only one of them. Of course, if you want to emphasize it, there could be different ones. They could have different means. For mean 0, mean 5. We write it like this. Both of these have variance 1. It's a choice to write sigma squared in the way we write it. But they have different means. Mean 0 and mean 5. It could also be 3 different normal distributions, all of them with mean 0. So the mu is 0, but I have 3 different sigmas. I bet that this one probably has sigma equal to 1, and then this one has a larger or smaller sigma? Smaller, right? It's actually like this, and this one has a larger sigma, has a larger spread. Let me just, in danger of confusing you a little bit here, think about what happens if I make the sigma even smaller, right? What if I make even smaller than the blue one? If I press it even more, what happens when I press the density function like that? I mean, it becomes taller and taller, right? And if I press it enough, I could actually hit a density function much, much larger than 1. That's maybe confusing, but if you think about it with the math way, it's pretty obvious that if the area under the curve should be 1, then if I make a curve on a very, very narrow interval, then of course it has to be above 1 to integrate to 1. This is just to make very explicit that the density function values themselves are not probabilities. It's only areas under the curve, under the density, that are probabilities. So, the standard normal, as I told you, is this one. Actually, what I've also told you is this statement, that an arbitrarily normal distribution can always be changed to a standard normal one if you want. By subtracting the mean and dividing by the standard deviation, this we can use for sort of hand calculation stuff sometimes. And it was used very much in the old days, and probably we're still a little bit affected by that, because in the old days the only access to the normal function was by means of tables in a book. I mean, a table that you look up in a book, and it was very difficult to make tables for all choices of mu and sigma. So you could just make a table for the standard normal, and then you could get everything from that. And maybe I have to admit that some of what I force you to do is a little bit affected of these old days situation. Nowadays we can use the R for any of those, so anyway we don't have to worry too much about that issue. But for the understanding of it, it's still pretty nice to have this feeling of that there is only one normal distribution actually. Just by changing the scale and the position and the scale, we can jump between any normal distribution. That's a good feeling to have still. So I think it's okay that we still practice it a little bit. So let's try the basic thing here. The standard normal is a model for many things, and as you will see in the rest of the course, for very many things in statistics. That's why it's so much used, and also probably why it's called the normal distribution in the first place. Anyway, let's use it as a direct model for some phenomena that we might want to know about. For instance, we do weight measurements, and we believe that our weight measurements are not exact. They are random. They come with a certain measurement error. We model that measurement error for now by a standard normal distribution. So on average, our weight measurements are correct. The bias is 0 if you want. I mean, they are on target on average, but they come with a variability of 1. So we should try to think about what could happen. What is the probability that when we weigh a certain piece, that it weighs at least 2 grams too little? What does that mean? Now whenever we do something like that, at least 2 grams too little. I translate it into this statement. Hey, I made the question, so I can translate it. I hope I agree with myself. I didn't quite agree, actually, because I'm a sloppy guy. Do you see how I was sloppy here? I wrote like this, set less than -2, because I think that was the way it was set. Maybe if you're more careful about what I put in the words, I should have written like this. Less than or equal -2 would probably be a more correct interpretation. But I'm a lazy guy, I'm a sloppy guy, so I don't care about these today, and that's what I said last time. When we are in the discrete world, it's not okay to be sloppy. Of course, I shouldn't stand here and say it's okay to be sloppy, but as an engineer from DTU, we are never sloppy, of course. But it's just to make a little point that it's important in the discrete world to know whether you want to include the -2 or not. But in the continuous world, the -2 point itself doesn't have any mass, it doesn't bring anything. It's a 0 thing, so whether I write it or not, it doesn't change anything. What you don't see is the P norm minus 2 here. That is the way to call that thing in R. There is the standard normal function, distribution function is in R, and it's called P norm. And if we plug in the minus 2, we get this approximate 2.3% value here. Here it's put in a plot. Remember this. For some points we're going to make, even though it's a bit, little bit, pushing it a little bit, but still if we are to round it to half probabilities, it would be 2.5, that would be the closest one. What about this question? What is the probability that the weight measures at least 2 grams too much? Before I was in the left side, now I'm asking about the right side of the normal. The normal is symmetric, so we already knew the answer, if we remember the information about the normal being symmetric. So, approximately 2.5% out there. Let's try to find this one. What is the probability that the weight measures at most 1 plus minus 1 gram wrong? And I'm doing a bit fast now. At most, which means not more than 1 plus minus 1 gram wrong. Here are 2 different ways of saying it. What is the probability that I'm within plus minus 1 of the right answer? That's the third way of saying it. It can be found by taking the probability of being less than or equal to 1. That's the one I have shown on the picture. Then I subtract the probability of being less than or equal to minus 1, and I'm left with the answer 68%. Right? The answer being between plus and minus 1 is between plus minus 1 is 68%. Let's, the other example 3 we take after the break, and instead let's go to back to this one. What I have actually showed you is more or less what they show in this picture also. That when you have a normal distribution, remember what I just did, the standard deviation was 1 in my example. Plus, within plus minus 2, remember my 2.5%, my answers that I showed you? I have, when I go 2 standard deviation away from the mean, there's only 2.5% left in the normal distribution. That's what I showed you, at least for the standard. And I also claim to you that it's the same for the other ones if I do this change between the standard and the general one. So, within plus minus 2 standard deviations, I have 95% of what's going on. So if I put that on this model, it would be within, and they claim that the model for our IQ scores has a standard deviation of 15. So mean of 100, standard deviation of 15. When you say that, you also say that I have 95% approximately. They say 96, that's due to my rounding thing that I showed you. Let's stick with the 95. The 95% of people are within 70 and 130. That's the model of IQ. That's what it says, if you believe it. I also found that within plus minus 1 standard deviation, that's the interpretation of 1 standard deviation. Means within plus minus 1 standard deviation, approximately 2/3 of us are within plus minus 1 standard deviation. So 2/3 of us would be within between 85 and 115 in this case, right? So that's the way that I take these probability statements that I have now taught you about the normal, and I use them when I look at the normal distribution as a way to tell a story about a population or a random phenomenon in front of us. So, just to keep you active also your brains during the break. I'm gonna share with you this little exercise here and quiz. One of them is just a check thing. And actually, let me just... actually, you may not quite be able to solve it yet until I've given you a little bit more after the break. So we'll get back to it. I'm asking you two things. A little check thing, that's the second question about whether you listened in. And we can have a chat about that at the end or sometime during the next lecture. And then we should try, if we, based on what I'm going to teach you now and a few minutes into next lecture, we're going to see how many geniuses we have, high geniuses we would have in Denmark, according to this model. But hey, that's for after the break, so let's do 15 minutes break now.